Nice. Can you hear me?
Yes.
Good. I'm Lucas, and I'll be speaking about application-specific rollups and how I think they could take us back to the future. So in the beginning, we had app-specific layer ones. They would only do one thing, which was usually money. They were not composable, and you had to bootstrap your own network of validators if you wanted to make your own app. And they were also kind of slow if you wanted them to be secure. Then Ethereum and other general purpose layer 2s came along, and they were still kind of slow, but you could do many things, and then you could make those things interact with each other. You would have composability. And you would just have to make your own app, and you would just get all of the security. Then, now we're getting rollups, which still have those desirable properties to a large extent, but they're fast. So I was thinking, what if we go back and explore the past, but only in this direction? And we do something like app-specific rollups. So how would an app-specific rollup look like? Well, I think it's interesting to look at the history of computing. At the beginning, we had app-specific circuits. Those are like actual circuits, not ZK circuits. Then we had general-purpose processors. And what we have now, if you look at an iPhone, is it still has like a general CPU, but it has a bunch of other stuff. It's like a CPU, a neural engine, which are application-specific, and they enhance it so you can do things that it wouldn't be able to do otherwise. So what if we apply the same scheme to app-specific rollups? And we still maintain those like nice properties of rollups, like composability, security, and throughput, but we enhance them so that they become better at certain things. So I built one such app-specific rollup, and it has not one, but two enhancements, which I'm going to briefly explain, then I'm going to show you, and then I will elaborate more. So the first, this is built on top of optimism Bedrock, which I will also speak about more later. So first, there's this thing called ticking, which you'll see in a later presentation as well. That's the idea of having a chain that calls a function every block as part of the protocol. So instead of having to have someone send a transaction, it gets called and it's enforced just by the execution of the client. The next is Conway's Game of Life, which, if you don't know, looks something like this. So it's a simulation with a grid. There's some cells that can be dead or alive. And then there's some simple rules that determine if like a cell becomes dead or alive based on its state and the cells around it. So what I've done is I've built these rules into the protocol. So instead of like executing as part of EVM bytecode, it's just like native code. So think Golang instead of Solidity. Now I'll show you my demo. It's built on math, by the way. Okay, so this Conway's Game of Life on chain. The state is held on chain, but the transition is also on chain. As you can see, it looks a bit boring now because it's been running for a very long time, so it's kind of stabilized. But we can zoom in and play some stuff. Now we send all of this in a transaction. Okay, that was a bit lame. I'm going to do a more beautiful one. Let's see.
Yeah.
Yes, very nice. Okay, so as you can see, this is like the chain is 1 block per second, but this is like ticking at like 2 frames per second because like every block computes the simulation twice, and then it just like gives you the data, and the client makes it look like there's some space in there. Let's see. Back to my presentation. Okay, so how does this work? So first, I'll explain the game of life thing. It uses this thing called precompiles. Precompiles are a native code that can be called from the EVM to execute an operation faster than a regular smart contract would. So it's this concept of like implementing something in Go, and then you can just call it from Solidity, oversimplifying things. And the thing is, Ethereum already uses precompiles. So if you do something like SHA-256 or like elliptic curve recovery, you are using precompiles. The thing is that Solidity abstracts you away from it. The thing is, I first built like the same demo but smaller, just like 70 by 70 tiles, just using Solidity and like a normal smart contract. And it was like super resource intensive. Like, this is my CPU. Like actually the CPU of the server uses one full CPU, and like the chain crashed afterwards. Now I do the same thing, but I do it bigger, and I do it with precompiles. And then the board has like over 10 times more tiles, but there's 1/10 of the CPU usage. So it's 1 order of magnitude bigger and 1 order of magnitude more efficient. So like 2 orders of magnitude better just by using precompiles. Now let's go back to ticking. As you saw in the demo, there's like the things move even if I'm not sending any transaction, because there's like this thing that gets triggered by the chain automatically. So how does that work? How is that possible? Well, there's this thing called Optimism Bedrock, which is the next generation rollup architecture that's based on principles of like simplicity, modularity, and reusability. And Optimism Bedrock has this very interesting thing. It has a special type of transaction, and actually a special type of special transaction called the layer 1 attribute system transaction. What that's used for is to like set in layer 2 like attributes of layer 1, like the block hash number and so on. So there's like this injected transaction as part of the protocol called this like hard-coded contract and set these attributes. And what's interesting is it's included at the beginning of every block. It doesn't pay for gas. It cannot be front run. So if you're trying to do something like I was trying to do, it's like very convenient. So what if we get the same thing and we just add another one of these system transactions, but instead of like doing the attribute thing, it just calls a contract that I can use to call some other like arbitrary contract. So in my demo, what this does, it just like calls a contract that just like makes the simulation go forward. Of course, ticking has its shortcomings. The good thing is you don't pay for gas, but the bad thing is you don't pay for gas. So you have to figure out some other way to like limit the resources the node is going to use, because even if you don't pay for it, it still takes compute to like compute stuff. And also, if you want to have multiple apps, so you can have atomic composability, and you want to have all of those in like this special modified chain, you have to figure out some way to like allocate ticking power to each of them, which of course has like a lot of complexity. So there's some more thoughts I have about how the future looks like. So of course the obvious is just like add more precompiles. Let's say we want to do like more like faster ZK or like more machine learning on chain. We just like add functions that can do that very fast and just like see what apps people build. But I think we can go even further. And the thing is, with precompiles, they're like pure functions in Solidity. They like compute stuff, but they don't read or change any state. So what if we can have this thing we call stateful precompiles, and we change the way things are stored on chain to things like spatially indexed databases, and we build like math games on top of it. I think that would be very interesting. Then there's this other like shower thought I had the other day, which is like building on-chain transaction pools. This wouldn't like replace normal transaction pools, but you can think of it as like one registry of actions you want to take that you put on chain, and then you use this ticking thing so that it like checks certain conditions and then executes those actions depending on the condition. And you can also have like programmable logic for like how these like executions get ordered instead of just like depending on like gas price and whatever the transaction pool does. So something you can do with that is like limit orders on chain. Now, if you want to make a swap, someone can come and like front run you, and you like pay more money than you wanted for some tokens. But if you just say, I want these tokens in exchange for these other tokens, and then you just have this ticking function executed if the conditions are right, and you can actually get this, then given that this like sticking function cannot be front run, you're like guaranteed that if the transaction executes, you will like get what you wanted. There will be like no MEV kind of like stealing from you, which is nice. If you want to check the live demo, it's like up there for you to use. That's it. Thank you very much.